We are working our way through the 4 steps in a test hypothesis. So far, we've identified a test in step 1. And in step 2, we have talked about the test statistic, the sample information. We're going to enter that sample data into our computer. We're going to get a number, and somehow we're going to have to evaluate this number. I mentioned in the last video how that number sometimes is what I call a gimme, an obvious number. If it's way out in the tail of the distribution you're working with, you know you're going to be rejecting H0. And if it's really close to the middle of that distribution, you know you're not. So sometimes this part isn't all that necessary, but most of the time we're going to want to evaluate that test statistic. And there's actually 2 different techniques to do that. And I'm going to go through the first technique rather quickly because it's not the technique that I'm going to recommend you use, and I'll explain why. So the first technique is called a rejection region. And a rejection region is a very distribution-based technique. In other words, based upon the alternative and what we're testing, we know what to expect from a distribution perspective. We know that if we take a large sample, in a lot of cases, we end up with a Z distribution. Small samples yield T distributions. We're going to run into Fs and chi-square. We know what kind of data set, what kind of data distribution we would expect through this process. And because of that, we can go to a statistical table, a Z table, a T table, an F table, a chi-square table, and come up with what's reasonably expected and what's not expected. And the rejection region tells us what's not expected. So if you're doing a test for a single population mean and you have a large sample, the example I have here, at alpha equal 0.05, we reject if Z is greater than 1.645. There was a time in your statistical lives where you would be able to go to a Z distribution, put 0.05 in the tail of the distribution. If you were doing an upper tail test, you would do this, and you would be able to come up with this cutoff point, the 1.645. That's what the rejection region looks like. Another example, at alpha equal 0.05, we reject if t is greater than 1.45 or less than negative 1.2 or 2.145. That's true if you're working with a sample of 15, you have a 2-tailed test, and the population you're sampling from is approximately normal. These are just examples of what rejection regions look like. They are rules for determining when you can reject H0, and they're extremely useful. They also require you to be familiar with Z distributions and T distributions, and later on in the semester, chi-square distributions and F distributions, and they require us to use statistical tables. And they work great, and there's nothing wrong with that. But there's an easier way. There's another way of making conclusions in a test hypothesis that's easier, better. Did I mention it's easier? And that's the way that we're going to rely on. Okay, so this is a way. The reason I mention this is because a lot of you guys may remember doing rejection regions, and depending who you had in your Stat 1 class, some of you may only remember using rejection regions, and that's all you know. Well, what I want to do is show you a second way. And the second way involves something called observed significance levels, or what are called p-values. And p-values take a look at that curve, that distribution, that Z, that T, that F, that chi-square, whatever it is you're working with, and give us the probability of seeing something even further out than what we observed, even more extreme than the one we observed. So the test statistic and the rejection region kind of work together to figure out, is the test statistic beyond that cutoff point? We call it a critical value. That's how you work with rejection regions. The p-value approach says, what's the chance of getting something further out there? And the smaller that chance is, the smaller that p-value is, the more crazy our test statistic looks. The more, the word I'll use, the smaller the p-value, the more contradictory that p-value looks. Remember in step 1 we talked about we're assuming the null is true until we reach a contradiction, until we can say there's evidence to suggest that the alternative is true. Well, a small p-value would give us that evidence, would say, we don't believe the null hypothesis. One of the reasons we like p-values so much, there's actually a couple reasons. One is they're easy to interpret. Some of you guys remember handy little ways of remembering this. If alpha is greater than the p-value, we can reject H0. If alpha is less than the p-value, we fail to reject. An easy way to remember it, if p is low, So if the p-value is low relative to the null hypothesis, if p is low, reject the hoe. And of course I'll say the null hypothesis, but it doesn't rhyme as nicely, does it? When p is low, reject the null hypothesis. It's an easy little tool, an easy way of remembering how to interpret p-values. Well, I'm a big fan of p-values for more reasons than one, but one of the reasons I like the p-value approach is it always gives us the same conclusion as the rejection regions. The approach is irrelevant. I'm a fan of p-values. I mentioned it's easier. I'm hopefully going to stress that point in just a second. But we're always going to get the same conclusion. It doesn't matter if you're talking about large sample, small sample, it doesn't matter. The rejection region, the p-value, as long as you're using the same alpha, you're going to make the same conclusion. So the decision as to which technique to use, it's not like, oh, that one gives you better decisions than the other one. No, they give you the same conclusions all the time. It's a matter of what's easier. Why is it easier? That's a pretty good one right there, right? What this allows me to do is say, let's put those tables aside. Let's not worry so much about z distributions and t distributions. Let's go get p-values. Let's use p-values to make conclusions because it's going to be easier. The computer's really good at math, really good. And the test statistic is calculated on the computer. That's why I can say, don't worry about the formulas. Let the computer do that for you. But the p-values is calculated from the test statistic. I'm going to show you a picture in just a second. And so if the computer can figure out the test statistic for us and it knows what distribution to use, it can tell us that probability as well. And so test statistics and p-values are a team. We get both of them on the printouts. And so that's what we're going to use. Now the other reason I like p-values so much is the p-values, this little interpretation here. Learn that one, baby. And actually it's probably this guy right here. Learn how to use that because it works not only for z distributions and t distributions, but it works in upper tail tests, lower tail tests, two-tailed tests. It works for Fs, it works for chi-scores. Every time there's a test hypothesis, this interpretation will work. So will the rejection region. The rejection region works all over the place too. It's just with the rejection region, you got to remember which distribution am I working with. Some of them have degrees of freedom. Some of them actually have numerator degrees of freedom and denominator degrees of freedom. You have to remember which tail or tails am I in. What am I? Or you can remember when P is low, reject the hoe. Completely your call. I'm just not going to give you any tables to work with. So that's sort of my call. P-values are the way to go. It's a smarter, better, easier way. Very rarely does the smarter equate to the easier. And in this case it does. So we're going to work with that. Now the way I want to work with the p-values is I want to show you a picture. And there's actually a couple pieces that I need to talk about with p-values. One is I want to take a look at this picture. And then I want to talk a little bit about, there is some things to think about with p-values. So in this example, let's suppose we have a large sample. Mu is 100. The test statistic is 1.96. Really all I want to do is get this picture on the board. This is a z distribution. I want to explain to you how the p-value and the test statistic and the rejection region, all that stuff's tied together. With rejection regions, okay, so the technique you may or may not remember, you would take your alpha and put it in a tail. Now, the way that you would do that is based upon which tail you're working in. If you have a greater than test, and this should be H naught here. Sorry about that. Let's assume that H naught is mu is equal to 100. Let's say HA is mu greater than 100. Oof, that's rough, but you get it with my picture there. We would go and we would put our alpha in the upper tail. So we'd come out here and whatever alpha is, we'd put alpha in here. And we would call this guy Z subscripted with alpha. Okay? And we'd say the way that we would write our rejection rate, at alpha we would reject if our test statistic fall further down the tail. So let me change colors here. Let's go with something darker here. There we go. Let's say that our test statistic fell out there. And technically the alpha extends out here. Okay. So if that was our test statistic, we would compare these two things. That's how we work with rejection regions. And we would say because the test statistic is further out, we reject. Now what I want to show you is how the p-value works. In the p-value, we take a look at our test statistic, and remember the test statistic is calculated for us on the printout, and then the probability of getting something even further out there, well, that probability in this case, in a greater than case, would be this shaded region out here. And so this purple, I think you can see this is a purple pen if I'm seeing my colors correctly, this would be the p-value. The red shaded region, that's our alpha. And so if I ask you the relationship between the p-value and alpha, you'd say the p-value is less than alpha. P is low, we can reject. So both conclusions are going to give us this, or both techniques are going to give us the same conclusion. If I had a less than test, everything would flip around and be on the other side, but it'd be the same picture just with negative signs attached to the z value here and the test statistic here. If I have a not equal to, everything gets halved and you have it in both sides, but it's the same idea. It's just the purple values here, the p-value and the test statistic, are going to show up on the printout. If you decide to use rejection regions, you'd be responsible for finding this guy. I'm taking that away from you. That's a good thing, by the way. I'm saying you don't have to worry about that. We're going to use p-values this semester. Now, here is something I want to talk about because it's an issue. As your direction changes, let's say that this is a greater than test. What if I was doing a not equal to test? This does play a role in some of the things we're going to think about. And I'm going to specifically make a video talking about p-values and our computer software for you to consider. Okay? Here's the question I have for you. If we were doing a not equal to, so let me put the mu in here. If that was our alternative, and I asked for the p-value, what would it look like? The picture I have in front of you here, this test statistic, what's further out there? Remember, the p-value gives me the probability more contradictory. Well, if you're looking in the right-hand side, if you're doing a greater than test, all our attention's in the right-hand tail. Test statistics further out would be more contradictory. But what if all of a sudden someone said, wait a second, you're looking in both tails? Well, what's further out here than this test statistic? Well, surely this tail is still further out here, but you know what? I'm going to come over here and I'm going to put the negative of that value. And what's further out? Well, this is further out here as well. So the p-value, and the computer's real good at figuring this stuff out, by the way, but the p-value is going to be specific to the alternative. If you have a two-tailed p-value, these two pieces over here, this guy and that guy, are part of the p-value. And so the question is, what's the relationship here? What's the relationship of the p-value in the one-tailed test to the two-tailed test? In the one-tailed test, it would just be this side over here, and I guess I should probably do it that way. In the two-tailed test, it's both these sides together. Can you see it? Can you see that the two-tailed p-value is twice the one-tailed p-value? And it all depends upon which direction you're looking. That's going to be important. That's going to be real important for us because sometimes, not often, but sometimes the computer, and depending what software you use, the software I use typically does a good job of letting you choose the alternative hypothesis. Sometimes the software doesn't. And when it doesn't, if you have a choice to make and it doesn't give you that choice, it's going to assume you're doing a not equal to p-value or a not equal to test, and you're going to get the two-sided p-value. Okay, so you got to be careful. If the p-value that you want doesn't match what you're given, you need to adjust it. If a two-tailed test was conducted on the printout, but you want the one-tailed p-value, how do you go from a two-tailed to a one-tailed? How do you go from both sides to just one? Well, you take that p-value and divide it in half. Now, it's not a big issue. I make it a bigger issue, I think, sometimes than it is. It doesn't occur very often. But there is one time that we're going to run into this semester where I know it will occur. There's no way around it. When we're doing our regression analysis, especially our simple linear regression analysis, we're trying to relate a variable x to another variable y. We're trying to predict the sales price of a house based on the size of the house. Well, I think most of us would agree bigger houses are going to sell for more money. There's a positive correlation. There's a positive relationship, and we're going to test for a positive slope in our regression line. Yet the test we're going to conduct always tests to see if there's any slope. It's going to look for positive and negative. We don't care about the negative. We only want to do a one-tailed test, but we're going to get a two-tailed p-value. And so before we interpret that p-value, we need to adjust it. We're going to need to split it in half and then look to see if it's low. So get the p-value. The moral of the story here is get the p-value from the printout you're working with. If you have to divide it by 2, so be. If you have to double it, maybe you wanted the two-tailed and I mistakenly gave you the one-tailed. But look to see what the p-value is and then compare it to alpha. If p is low, you can reject the null hypothesis. So, assuming we can get the p-value that we want on the printout, all we got to do is compare it to alpha. If we can't, we may need to adjust it before comparing it to alpha. And so that's our second method. Computer does most of the work here. Sometimes we divide by 2. Ooh. Computer's going to do the heavy lifting for us. And we're going to take the results and we're going to compare it to alpha to make our conclusion. So 2 different techniques for say, let's say evaluating a test statistic: rejection regions, that's old school, that's kind of the approach from yesteryear, and the p-values, that's a smarter, wiser technique, and that's what we're going to use. So get to work on that. Take a look at some of the problems and quizzes and projects and fun stuff I've got for you, and you know how to get hold of us if you have questions. So long.